In this video, we talk about one example of a linear data transformation, which is Schmidt orthogonalization. The Schmidt orthogonalization is the easiest one to understand, and this is why we talk about it, but it's not the widely used one in machine learning and so on. So you can use it, but if you let Schmidt orthogonalization go and use other ones, you may benefit other properties that the other one may have. This one is one example. So Schmidt orthogonalization is that you have a set of vectors and then you orthogonalize them one by one. In this case, we have a set of linearly dependent data. We want to form a set of orthogonal samples. So we want to, these dependent data, we want to remove the dependency and form a Cartesian coordinate from these vectors. Remember that random variables are random vectors, and so we want to decompose them and then remove the redundancy. So what we do, Schmidt sequentially makes these, produces these ones. So the first step is a normalization. So you get the first random vector and then divide it by its length. So I1, length of I1, the random variable, is equal to 1. So remember that norm of a random variable here to the power of 2 is mean of x to the power of 2. Here, assume that the mean are 0. They are 0 mean random variable for simplicity. If they are not, you can. So the second step, you take the second random variable. So this is your x1, and then whatever is this length, which is equal to a square root of mean of x 1 to the power of 2. So then you get I1. The first random variable has a length of equal 1. So it has a length equal 1 is equal to x1 divided by its length. Then you look at the second random variable, which is, let's say you have x2, and then from x2 you find, you project x2 on this direction. So this is a unitary vector in this direction. So you are looking for a vector which is perpendicular to I1, but it is on the same space. So you have x2 and I1, they form, so let's say x2 is gone. So I forget about x2. I have I1 and x2. Okay, and these I1, I'm at step 2. I1 is a unitary vector. So x2 is decomposed in two components. One component is along the direction of I1. So this is called projection of x2 on the direction of I1, and then the other one is projection of x2 on the direction of I1 but orthogonal to I1. Okay, so obviously if you add this vector, plus this vector, if you add these two, you get vector x2. So because I already have I1, I ignore this one and I consider this one. So this vector, orthogonal projection of x2 over the direction of I1 is equal to just x2 minus expected value of x2 I1 times I1. Okay, so so the second step is that from x2 and I2, I find these orthogonal projection. Okay, and then this vector, and then I orthogonalize it. So if this vector is 0, I cannot normalize it to its length. So it has some length because I want a vector along this direction, but I want it to have a unitary length. I want this length to be 1. So whatever is this vector, I divide it by its length. So this is the orthogonal projection of x2 over I1. And I divide it by its, whatever it is on its length, to find a unitary vector I2. Okay? And then I can continue. So to find these I2, I need 2 steps. Orthogonal projection and normalization. Orthogonal projection and normalization. And if one of these vectors becomes 0, I skip it. I go to the next one. So iteratively, I could find In and so on. So if some of them are 0, I will obtain less orthogonal unitary random variables compared to the number of inputs. So remember that length of a random variable is a square root of x to the power 2. So obviously you can see that if one of these orthogonal projection is 0, we skip and we go to the next one. So we skip xn, and then this means that remember that xn always is a linear combination of ii's, which is a linear combination of i. So it means that using I1, I could produce x1, and using I1 and I2, I could produce x2, I1, I2, and 3, I could produce x3, etc. So using these random variables, I could get my input data back. So when this system of Gram-Schmidt orthogonalization, I get x1, x2 as input, and the output gives me I1 and then In, but using the output, I can't get the input back. So it's one-to-one relationship. So I'm not losing any information. But what I'm obtaining is that these components, the output components, are orthogonal to each other. So the number of ik can be less than or equal n. So somehow you are reducing your data, and you get your inputs. So interestingly, I and ik, they are orthogonal. See, if I and k are not equal, they are perpendicular, and length of all of them is equal to 1. So from what we said, you can calculate x1 using this one and so on. And if you write this one in a matrix form, so you could have this is your innovation vector, this is your input vector, the innovation or output vector, and obviously x is equal to L times I. So I is equal to L inverse times x, and this is your Gram-Schmidt orthogonalization matrix, and x is equal to L times I, and remember that this is lower diagonal matrix. And it is easy also to prove that this matrix, the autocorrelation matrix of the innovation or output vector, is identity matrix, and this one is RXX. So it's kind of like triangular decomposition of your matrix. So if you have a covariance matrix, this is a lower triangular matrix, the upper triangular matrix. So this is known, if this decomposition is known as Cholesky factorization matrix. So if you have the RXX, if you give it to MATLAB with Cholesky factorization, it's going to give you very quickly L. So it's a fast computation.